Okay, in part one of the observational properties of stars, we talked about two ways of determining the surface temperature of a star. We said we can find the peak of its spectrum through spectroscopy, and then by finding the peak wavelength at which it has the greatest emission, we can use Wien's law to figure out the temperature. In practice, that is hardly ever done because it's a very tedious process and fraught with difficulty. A more common technique is to use different color filters and measure the brightness of the star, for example, in the blue and the visible and the red. In comparing those colors and taking their ratios, we can get a very, very good idea of which stars are the hottest, which ones are the bluest, for example, which ones are the coolest, the reddest stars, and the ones in between, the sort of yellowish or green stars, which actually look more white, but are brightest in the sort of yellowish-green area of the spectrum. Okay. Now, once we determine the temperature of stars, we want to classify them. And astronomers use what seems to be a very silly, very ad hoc classification sequence. It's called the spectral sequence because commonly we use spectra to determine temperature. And the letters seem to be pretty much random. O, B, A, F, G, K, M. Okay, O, B, A, F, G, K, M. These are letters that all astronomers know. The fact that you folks are not astronomers makes it a little more difficult. So there's this very silly mnemonic device to remember this by. And every astronomer knows this. Every astronomer remembers the silly mnemonic from when they were in school. We are going to use the non-sexist version, or at least the equal opportunity version of this this mnemonic device. It's O, be a fine girl or guy, kiss me. O, be a fine girl or guy, kiss me. You won't be able to forget this once you learn it. The other thing is you can make up your own mnemonic if you wish. You had a contest on this a few years ago, and the best one that I can remember. There was one very good one about frogs, but I can't remember it. But the best one that I remember was, "Oh boy, astronomy final's going to kill me." So at any rate, be my guest just to try to figure out another mnemonic if you wish. Now, those two methods that I talked about earlier do not always work. Finding the color of a star and finding the peak wavelength of a star is not in practice always possible to determine its temperature. And the reason is our galaxy is a dusty place, and dust can alter the color of starlight between the star and our eyes. So we talked about before the intensity curve of a star, a thermal black-body curve, say 58,000 degrees. So this, for example, would be like the temperature of the sun. And this would be a rough idea of the spectrum of the sun. Now, the thing is, if we were looking at the sun through many, many light years of our galaxy's plane, it turns out the sunlight would pass through a lot of dust. This also, a very similar thing happens. It's not exactly the same thing because it's our atmosphere and not intergalactic space. But a similar thing happens when the sun is rising or setting. When you have sunrise or sunset, sunlight will pass through a column of air that is fraught with a lot of dust. And dust tends to scatter the blue end of the spectrum, the blue and violets and greens, and it tends to let the long wavelength light, the yellows and oranges and reds, those colors kind of wiggle around the dust particles and they don't get scattered. So what that means is if the sun had a lot of dust in between us and it, for example, when the sun is setting, or if we were far away in the galaxy and the sun was behind a great deal of dust in our galactic plane, we would see a lot of this light here on the red end of the spectrum, but a lot of this light on the blue end of the spectrum would be diminished. Okay, it would be lessened tremendously. And so because of that, the sun would look redder than it is. And in fact, that's what happens when the sun is rising or setting. The sun when it's high overhead on a nice clear day, seems to look white. We see all the colors of the spectrum. But if we took away some of the blue part of the sun spectrum and the yellow, or rather the green and the violet, the sun would look redder. And that's exactly what happens when the sun is setting, because of the dust acting like a colored filter. So if we were to estimate the temperature of the sun just by looking at the sun when it's rising or setting, we would underestimate the surface temperature. We would say, oh, it's not 5,800 degrees. It's only maybe 4,000 degrees or 4,500 degrees. That's the problem we have with distant stars within our galaxy. Okay? So the continuous spectrum of distant stars is altered by interstellar dust. Okay? The dust scatters the blue photons more than the red ones. This is why sunsets are red, although be cautious about this. This is because of dust within our atmosphere, not dust within our galaxy. Okay, the rising and setting sun has nothing to do with dust within our galaxy, but it's still dust, and dust tends to act like a color filter, letting the long wavelengths through and making the short wavelengths scatter in different directions. Okay. This, of course, is called interstellar reddening. Interstellar reddening because the blue end of the spectrum is reduced by scattering. Now, you might say, well, okay, now what do we do? If we have distant stars, how do we figure out the temperature of these stars? Well, luckily, nature has given us a third way of figuring out the temperature of stars. And this is by the darkness, or the intensity, or the strength of the dark absorption lines in a star spectrum. You may remember from the chapter on spectroscopy that, in fact, the absorption lines of a star has absorption lines, and the reason it has absorption lines is because there are cooler gases in the star's atmosphere, and those cooler gases absorb some of the fine colors of the continuous spectrum, the rainbow type spectrum, from the star's hot, dense surface. Okay? So let's take a look now at a bunch of spectra of different stars. O, B, and A stars are the really, really hot stars. Okay? And G, K, and M stars are the cooler stars. And F stars are right about in the middle. Okay. So that spectral sequence, those silly letters that we went through, are all related to the star's temperature. So O and B stars, what you should sort of commit to memory here, O and B stars are the really hot stars. They're the hot blue stars. K and M stars are the puny little cool dim stars. And A, F, and G stars are sort of mid-range stars. Okay. Now, if you look here, this is the hydrogen beta line, or the Balmer beta line. Okay. You may or may not remember from the chapter on spectroscopy that this is caused by electrons jumping to or from the second level. In fact, it's an absorption line, so that means the electrons are actually jumping up from the second level. Okay. Here also are the hydrogen alpha lines. This is the jump from the second level to the third, and this one is the jump from the second level to the fourth level of hydrogen. And in fact, this one here, H gamma, is the jump from the second level to the fifth level, and so on. Now, the weird thing is, stars are made primarily of hydrogen. So you would expect all of these stars to have very dark hydrogen Balmer lines. But in fact, they don't. Okay? Our sun, for example, is a G star, and it has very puny Balmer lines. Okay? And it has stronger sodium lines, in fact, than it has Balmer lines, even though 90% of the sun's atoms are, in fact, hydrogen. And that's interesting, and it's actually useful for us for figuring out temperature. Because as you can see, cool stars, or not so hot stars like our sun, have fairly wimpy, non-distinct hydrogen lines, Balmer lines, And really, really hot stars also have non-distinct hydrogen lines. But medium hot stars, stars around 11,000, 12,000, 13,000 degrees, have very, very strong dark hydrogen lines. In fact, if you were to measure the strength or darkness of these absorption lines, you'd find that they seem to be very, very closely related to the temperature, the surface temperature of the star, because the surface temperature is also related to the atmospheric temperature of the star, since the atmosphere and the surface are right next to each other. Okay, if you were to draw a graph of the strength of these spectral lines, it would look something like this. Okay, so this has a whole bunch of different elements and spectral lines that you might see in a star spectrum, but let's just look at the purple one here. Hydrogen, okay, the line strength, meaning the darkness or thickness of the line, is greatest around an A star, okay, or a hot F star. That means around 11,000, 12,000 degrees Kelvin, okay. It gets weaker when you get to the really hot stars, the B and the O stars. There should be O star here at the end here. And then it also gets weaker as you get to F and G and K stars. Okay? So, why? What's the difference? Why is this the optimum temperature for hydrogen lines? Well, it's actually not so difficult. What we have to do is realize that Balmer absorption lines happen when electrons jump from the second level upward. So that dark line in the red part of the spectrum was the jump from here to here. The dark line in the blue-green part of the spectrum, the sort of teal-blue part of the spectrum, was the jump from here to here. The line in the violet part of the spectrum was from here to here. The only way you're going to get those dark lines is if you have atoms with a lot of electrons hanging out in this second level. So the second level has to have a large population of electrons in the atom. So if you got zillions and zillions of hydrogen atoms, and if a decent percentage of those hydrogen atoms are hot enough, they're banging into each other with enough energy to kick those electrons into the second level, then it's possible to have jumps from the lower level up here. So it's possible to have Balmer lines. When you talk about cool stars, like, for example, the sun and cooler, most of the electrons are hanging out at this ground level. Okay? And so, basically, you can't have the electrons jumping up from the second level up to make those dark Balmer lines because there aren't any electrons there. Okay? You can get Lyman lines, but those are in the ultraviolet. Okay, that's something that could be helpful, but something that we don't see very easily. The other thing is, really, really hot stars have electrons that are way up here, or electrons that have been ripped off completely from the atoms. And so the deal is, with the hot stars, the reason they have wimpy Balmer lines is the exact opposite of the reason that the cool stars have wimpy Balmer lines. For the cool stars, there's too many electrons hanging out in the ground state because it's just too cool. They're not excited enough to hang out in the upper levels. Okay? In the really hot stars, there's too many electrons in the upper levels, or too many that have been ripped off completely. And that means there's not going to be enough electrons in the second level. To have really dark Balmer lines, you have to have a lot of electrons in that second level. So basically, it's like this. A hot star's up here, you have wimpy Balmer lines because the temperature is too hot and the electrons have been ripped off from the atoms. In the cooler stars down here, the wimpy Balmer lines are not distinct because most of the electrons are down in the lower level and so can't make Balmer absorption lines. But this is the Goldilocks temperature. This is where the temperature is just right. This is where the temperature is just right to have enough electrons in that second level to make nice, dark, strong Balmer lines. And it's like that with all the other spectral lines as well, except they're much more difficult to understand. Okay. We will continue in part 3.